Hello there! I'm Haris Pigkaulan, and this is my colleagues by Putri Malang, Sahara Abdul, Yasraf Gindo, Nisa Maulana, Almansur Sanday, Miriam Abdullah. We're going to tackle the first law of thermodynamics. But first, we need to know what is thermodynamics. And this will be explained by Sahara Abdul.
The word thermodynamics comes from the Greek word thermos, which means heat, and dynamics, which means power. Instead of being grouped within the chemistry family, thermodynamics is part of the physics family. Essentially, thermodynamics is a science which studies the changes in temperature, pressure, and volume on physical systems on the macroscopic scale by analyzing the collective motion of their particles through observation and statistics, since heat implies energy in transit and movements is correlated with dynamics. Thermodynamics studies energy movement and how energy produces movement.
Before we tackle the first law of thermodynamics, we need to know the three fundamental concepts associated with heat. The first concept will be explained by Putri Malang.
The first fundamental concept in thermodynamics is heat transfer. What is heat transfer? In first law of thermodynamics, heat energy, a thermal energy, transfer from hot object to cold object. Why this transformation of heat energy happens between hot and cold objects? The answer is, there is no scientific explanation behind this transformation of heat energy from hot object to cold object. It is a natural process. Heat, a thermal energy, will transfer from hot object to cold object until the both of these objects will get an equal temperature.
The second concept will be explained by Yasraf Gindo.
Hello, Yasraf Gindo here, and we will start the discussion. Heat in work occurs every day of bringing energy into or taking out of the system. Though the processes are different, heat transfer a less organized process, driven by the temperature differences. Meanwhile, the work is organized process involving a microscopic force exerted through a distance, but both can produce the same results. Since both can cause an increased temperature, heat transfer it into the system. This is something like the sun warming up the air in a vehicle tire. That increases its temperature. And also the work is done in a system. It is also something like this. When the engine starts the tire to move. And once the temperature increase has occurred, it is impossible to tell whether it was caused by heat transfer or work. And this uncertainty is an important point. Heat transfer and work are both energy in transit. Neither is stored as such in a system. However, both can change the internal energy of a system, because internal energy is a form of energy completely different from either heat or work.
The third concept will be explained by Nisa Maulana.
Internal energy is known as the sum of a substance, molecular energy, kinetic and potential. In physics, that idea of internal energy is commonly correlated with gases. Two types of energy apply to all gases: kinetic energy and potential energy. Thus, the substance internal energy consists of two energies: kinetic energy and potential energy. The ideal gas is generally regarded as a working materials, is thermodynamics. It is assumed that gas molecules do not interfere with each other in the optimum gas. Therefore, among the ideal gas molecules, no potential energy is available. Therefore, only kinematic energy is the internal energy of the ideal gas. The internal energy of the ideal gas depends on the kinetic energy of the molecules.
So let's jump into the introduction of our topic, which is the first law of thermodynamics.
Hello, my name is Sahara Abdul, and we will discuss the first law of thermodynamics, or prominently known as conversion of energy. Therefore, energy cannot be created or be destroyed, but either transferred in two ways: work, energy, and power, and heat. Two of them are connected, right? As heat loses, it continues, but when work is done by a system, the heat increases. So, the heat is converted to work, and work is converted to heat. And together, the work and heat transferred into or out of the system represent the change in its internal energy, which is what we understand is the total kinetic and potential energy of all molecules in the system. And this phases occurs in an equation of internal energy is U, work is W, and heat is Q. The change in internal energy of a system will be equal to the energy transferred to or from the system as heat, minus the energy transferred to or from the system as work, and these quantities are measured in joules.
The history of the first law of thermodynamics will be explained by Almansur Sanday.
History of thermodynamics. In the late 18th and early 19th centuries, the scientist was adhered to caloric theory. Anthony Lavoisier in 1783 by his first proposal and further bolstered by the work of Sadi Carnot in 1824. American Physical Society believed that the caloric theory is a treated heat as a kind of fluid that naturally flowed from hot to cold regions, much as water flows from high to low places. When the caloric fluid flowed from hot into cold, it will be converted as a kinetic energy and made to the work, much as falling water could drive a water well. It was not until Rudolf Clausius published the kinetic mechanical theory of heat in 1876 that caloric theory was finally put to rest. So,
the heat engines in the first law of thermodynamics will be explained by no other than Sahara Abdul.
Application: heat engines. Heat engines is a device that converts heat into mechanical energy. They can be used for almost any purpose, and they are all around of us in most forms of transportation, generation of electric power, pumping of fluids, and movement of air. The engines that you commonly see every day converts gasoline or diesel fuel into heat, and in turn into mechanical energy. The energy delivered from a heat engine output is measured in how much work the engine can do, lifting a certain weight a certain distance in a period of time. This measurement can be arithmetically converted to watts, horsepower, or other units of work.
First, we need to know what is this sign conventions for us to know what is the possible sign of our heat and work in the problem. So Q is positive if the heat is added to the system. W is positive if work is done by the system. Q is negative if heat leaves the system. W is negative if work is done by the system. Hello guys, I'm Haris Pigkaulan. I am going to show you how to solve problem in our topic, which is the first law of thermodynamics using its equation. The equation of the first law of thermodynamics is initial energy is equals to heat minus work. So let's jump in for our first problem. 3,000 joule of heat is added to a system and 2,500 joule of work is done by the system. What is the change in internal energy of the system? First, we need to know what are the givens and what are we going to find. So, in the given, heat is equals to 3,000 joule and work is equals to 2,500 joule. So, we are going to find the change in internal energy of the system. So, here is the solution. As I said to the equation, you need to subtract the work to heat. So, initial energy is equals to 3,000 minus 2,500. Then, our initial energy is equals to 500 joule.